I will talk about how JavaScript performance compares to C++ performance and where WebAssembly fits into this performance discussion. There are lots of ways to improve performance, and earlier today we saw Nikolai's great talk, how they achieved a 10x improvement. I will not talk about any of the improvements that he was talking about. My talk focuses on the performance of the JavaScript runtime, of JavaScript itself. So we will not talk about file I/O or databases or HTTP requests or how you can improve performance with different rendering or frameworks. I will focus just on JavaScript itself and how it's being executed by the JavaScript compiler. And I'll compare that to the performance of the same algorithm implemented in C++ and compiled to WebAssembly. It's a performance talk, so I want to point out, never optimize prematurely. Always measure first. Don't go back on Monday and say, oh, I'll optimize something because I heard it's faster. No, no. Make sure you have a performance problem. Don't even start optimizing otherwise. And then measure really careful and find your bottlenecks, and only optimize your bottlenecks. Don't try to optimize other parts in the code that don't even matter for performance. You'll only introduce bugs and make it really hard to maintain. So be careful with any performance optimizations. Never do it prematurely. And then if you do measure and optimize something, keep measuring. Make sure that your performance doesn't get worse over time. Before we talk about performance, I want to point out some fundamental differences between dynamically typed scripting language JavaScript and a language like C++. So in JavaScript, if you want a property X on an object, you can just do that. You define an object, and then you set the property X, in this case to 42. Obviously, you could do that in one line, but you can just set your property. So how is this in C++? You can also have a property X in C++. But before you can set it, you first have to tell the C++ compiler the class of the object. So you have a class definition, something that sort of defines a type in C++. This is pretty much the only C++ we're doing today. No worries if you're not a C++ expert. I just want to show you that before you can set this X property in C++, you have to define the class. So once you've defined it, you can instantiate an object and then set X to it. So it's kind of like in JavaScript. But now in JavaScript, at any time later in your source code, you can say, oh, I forgot, I also need a Y. Not only X, but Y on this object X. You can do this at any time. It's gonna work, and you can use it later. If you try to do that in C++, this won't even compile. Because in C++, you have to tell the compiler first what you're going to do, what kind of type it's expecting. By defining this class in C++, you're setting out the memory layout for this object. So you cannot in C++ later on just randomly change properties. You have to make that very clear up front. And that property that you can do this at any time in JavaScript is called dynamically typed. It's very dynamic, it changes all the time, versus in C++, we refer to C++ as statically typed. It's very static. Once you start compiling or writing code, you cannot just change the properties. For us as developers, dynamic type languages can be really nice. They help us to get started very fast. We don't have to learn about all the different types and variables like we have to do in C++ before we can write the most simple function. It makes prototyping really fast. And also for working with things like JSON, dynamically typed languages are great. It would be really hard to parse a JSON string if you have a statically typed language, because you would need to know exactly what you get over the wire so that you could define that class. So dynamic typing can be really great, but from the point of view of a compiler, it has some drawbacks, because it's actually a lot of work, because instead of us defining it as up front, the compiler has to figure out what will happen. So look at this very simple property lookup. So we do this in JavaScript all the time. We look up a property on an object. As soon as you say console.log, you do a property lookup. You look up the property log of console. So it's all over your code. Super simple. You don't even think about it when you write it. But when you write that, when the compiler has to look up what's happening in this case, it's a lot of things that could happen. It could throw a type error. The property x could be undefined. X could be undefined on object, but be defined further up in the prototype chain. X could be a proxy with a get trap. Or you could have all kinds of side effects by looking up x if x was defined as an accessor descriptor. So this simple dot already has like lots of things that could happen in JavaScript. And in fact, if you look at the ECMAScript specification for property lookup, it's this really long list of 8 steps. Well, 8 steps is not really, really long, but actually every single one of those entries has 1 or 2 other lists that are just as long. So just doing object.x is this like maze through the JavaScript specification of figuring out what to do. And of course, a compiler who compiles JavaScript has to follow the ECMAScript specification. So it's really the compiler who has to do this maze of instructions from the specification every time you say console.log. So what's our intuition about performance for a scripting language like JavaScript? It's a scripting language, it's dynamically typed. The most simple syntax is already a ton of work for the compiler, not even talking about more complex operations. So what's our intuition here? It might be that we assume JavaScript is fairly slow, because we, the developers, don't do the work of predefining a type. We just say, something, types are dynamically changing, the JavaScript compiler will figure it out when I run the code. Let's look at some data. So I calculated prime numbers. It's not a sophisticated algorithm. It's just something to give me prime numbers. I calculated the first 1 million prime numbers. I did that in JavaScript, and then I implemented exactly the same algorithm in C++ and compiled it with optimization, and then compared the performance results here. And so JavaScript is the blue line, C++ is the red line. Yes, JavaScript is slower than C++, but by very, very little. This is less than a factor 2. So it's totally the same ballpark of performance that's happening here. And if you think about what I just told you, like all the steps the compiler has to look up when you do a property lookup according to the specification, this is absolutely amazing that the calculation of the prime numbers is almost as fast in JavaScript as in C++. So what's the trick that gives us this performance when we use a scripting language like JavaScript? So the trick that all modern JavaScript engines use, including V8, which is the engine in Node.js, is so-called just-in-time compilation, JIT compilation, just-in-time. It's sometimes also called lazy compilation, because the compiler compiles the source code just in time as it needs it. So it's very lazy. It's not doing all the work ahead of time and like getting everything ready and then running it. No, it's just in time, very lazily compiling a little bit and then running that compiled machine code, then compiling a little more as it needs it. So the just-in-time compilers, they alternate between compiling and executing the machine code. So whenever you have source code that you want to execute, it doesn't matter what language, you usually have a parser that parses the source code into an abstract syntax tree, an AST, abstract syntax tree, that is just a representation of your source code that's easier to work with by another computer program. So source code is for humans, AST is for another program, but it's just a different representation of what you had in source code. And then you have an interpreter or a compiler that takes this abstract syntax tree and generates executable machine code. So depending on the programming language and the context, this last step is sometimes called an interpreter, sometimes a compiler. It's a little fuzzy. There's no exact definition when it's which of those. So that's your typical compiler toolchain, but now for just-in-time compilers, it's not this linear line anymore. For just-in-time compilers, you get this loop at the end, the loop between just-in-time compilation and running some machine code, compilation and machine code, and so on. Okay, so that's what a just-in-time compiler is, and I just told you, oh, it makes JavaScript really fast. How can something that, instead of being a straight line, doing all the compilation work up front, and then being done with it, how can that be slower than like messily compiling, running, compiling, running? Well, the big trick or the big advantage of like alternating between those two things is that since we run the machine code early on, we can get feedback from runtime, some type information as we execute the code, and then use this information when we compile more code. So that's the whole trick here. We can, by running early, we can get information that we then use for more compilation. So JavaScript engines, they use feedback or information about types that they collect at runtime to speed up performance when they compile more code. And in modern engines, this is not enough to give you this really impressive performance that I just showed you. Modern engines have another trick. They all have at least two compilers. They have a baseline compiler, and then they have a second optimizing compiler. So the optimizing compiler, its job is to compile so-called hot functions, functions that have been executed a lot and that we speculate will be executed lots of more times in the future. The optimizing compiler recompiles those hot functions, and it's using, when it's recompiling them, even more information that we were able to collect when we executed this function in the past. And so by using this information, the machine code the optimizing compiler spits out is very specific to a certain speculation about the input, but it's also very fast. And if it turns out that what we speculated about what kind of data we will see in the future, if that speculation was wrong, it's not a big deal. We will de-optimize, we will bail out back to the baseline compiler. The optimizing compilers, so JavaScript is about 20 years old, I want to say, 23 years. And about 8 years ago, that's when we saw the first optimizing compiler. So V8 was, I think, the first major browser that had two compilers. And then in the following years, Microsoft Edge, Safari's WebKit, and Firefox JavaScript compilers, they all added other optimizing compilers to it because it worked so well for JavaScript performance. So only in the last 6 to 8 years is when the modern engines had this performance improvement. So here's this in a picture again. We have source code that the parser turns into an abstract syntax tree, and then the baseline compiler takes this abstract syntax tree and compiles the functions just in time as we need the functions, compiles them into machine code and runs this machine code. And while we execute the machine code, the compiler collects information about some of the inputs and some of the parameters, and it also collects information if a function is being run a lot, and if a function is identified as being hot, then that function goes to the optimizing compiler, which now recompiles this function and gives us better optimized machine code. And if the speculation that was used to optimize a hot function, if that turns out to be wrong at some point, then the compiler de-optimizes and bails out back to the baseline compiler. So here's a more specific example. It's a tiny little function add. It adds 1 to the property x of an object that you pass in. So very simple function. The very first time that we want to run this function, that's when the compiler says, oh, I don't know this function, I have to compile this function into machine code. And since there's a property lookup inside the function object.x, the compiler follows all the steps in the specification to generate machine code that matches exactly what the specification says should happen when you try to access a property. So it compiles machine code for this long, complex list of steps here. And eventually, it will figure out where in memory to find the value of x so that it can add 1 to this value. So in this example, the value obviously is 42. So since the compiler just did all this work of figuring out that the value of x is 42, or rather to figure out if the input is an object that has an x property, the value that it wants is at a certain position of the memory address of this object. Since the compiler just did all this work to figure this out, it actually saves that information in a little cache. And it's a cache of shortcuts, basically. So the keys are the type of the input, kind of like the class definition in C++, so the shape of this object. In our case, the shape is, it's an object that only has an X property. That's sort of your shape or type of this. That's the keys in this cache. And then the values are shortcuts on how to get to the value. So we're not putting in this particular object and the value is 42. No, we're putting in, if it's this shape of object, at this memory offset is where you will find the value for x. So that goes in this cache, and then the function returns 1 plus 42. And then we do some other calculations, and at some point we want to run this function again. And so this time, when the compiler needs to write machine code for this property lookup, it first checks the cache, and it's like, hey, do you have an entry for a key where the key is this object shape that just has an X property? And luckily we have that, so instead of going through all these steps here, we just know, oh, at this memory offset is where we will find the value. So in this case, 7. It's a different value, but the way to get it is the same offset as for the previous object. And we associate, we associate the cache with that particular call side of the property lookup. So every little dot in your source code probably has its own cache of shortcuts. Okay. So in our graph here, the baseline compiler compiles, when we first see the function, compiles machine code, and then when we are running this function many times and consider it hard, we pass it on to the optimizing compiler. And now the optimizing compiler uses exactly the information in the cache to generate optimized machine code. So in fact, the optimizing compiler, if there's one entry in the cache, then it only generates machine code that is valid for exactly this kind of key. And if you feed in something that doesn't match the keys in the cache, so here I'm not feeding in an object with an X, but with a Y, so the memory layout is totally different, so this shortcut from the cache would be wrong, it wouldn't give us the Y value. If you have this wrong speculation, if you generated optimized code using a speculation that is now not valid anymore, then you don't get wrong results. It's just that the compiler de-optimizes and bails out back to the baseline compiler. So to give you some idea about this generated machine code, those CPU instructions, here is the machine code for x86. And on the left-hand side, it's the output from the baseline compiler. And this actually runs on for a few more pages. So this is just for this tiny little add function, which said add 1 to every object. It's pages of instructions, because those instructions, they can only do small things, and you have to usually you need lots of instructions for like one simple JavaScript instruction. On the right-hand side is machine code for the same function, but generated by the optimizing compiler. And you can see it's way shorter. It's 4 lines. I want to quickly go over those 4 lines. It might look super complex, but it's really not. The first line, compare. It compares that the input matches that key that we saw in the cache, because the optimized code can only handle input if it is found in that cache. It was using the cache to be generated. So the first line, the compare, checks that the input matches the cache. And the second line, the bailout, it's a jump to bailout. Bailout means we are de-optimizing. So if the comparison didn't hold, then the next line says, okay, jump to the de-optimizer. If the comparison did hold, if we have input like we had all the time and it is a hit in the cache, then in the third line we move the X value into a register. And then the last line add, this is where we add 1 to the X value. So it's 4 instructions versus pages of instructions. And this is why you're seeing this massive speed up, because with the optimizing compiler, when you run JavaScript code, when you do this prime number calculation that I did, you're usually not in the left-hand side, you are in the beautiful land of the right-hand side, optimized compiler, very few instructions for the same output. If you want to play around with this, you totally can. You can pass V8 flags to Node. Just do node --traceopt server.js. And then you can do traceopt and tracedeopt. That will show you exactly when a function is being optimized. So you'll get quite a bit of output on your screen, but it will say optimizing function add. And later you might see de-optimizing function add because, and then there's some reason, for example, the input didn't fit the cache. You can also print the machine code if you want to see that, and you can trace the ICs. Those are these little caches associated with every call site. So when you run JavaScript, when you run Node, you always get the picture at the bottom. That's the same one I showed you earlier, where JavaScript is almost as fast as C++, less than a factor 2 slower. If you deliberately turn off the optimizing compiler with --no opt, then you get this picture at the top where it takes 80 seconds in JavaScript, but only 10 in C++. So obviously this is way slower, and if you wouldn't have the optimizing compiler, it would be much, much harder to use a big React framework or write a complex Node server, because everything would be 20 times slower than, or 10 times slower than what we have right now. And when you zoom in for the very small numbers, it's very interesting. So JavaScript, the blue line, is slower than C++, the red line. But for very small computations, JavaScript is actually a lot slower than C++. Like see for the first 50 primes how much slower the blue line is. And then it starts spiking, and all of a sudden JavaScript is almost as fast as C++. And you can really nicely see here how the optimizing compiler kicks in. You start with the baseline compiler. Information is collected that this prime function is being called a lot. So at some point, the prime function is passed to the optimizing compiler. And that's where the spikes are coming from, because now the compiler has to recompile the function. That takes a lot of time. And then once that's done, that's when you have this massive speed up, and you're almost at C++ level. OK. So I showed you JavaScript versus C++, and they're very similar in speed with modern browsers with Node.js. It's not 2010 anymore, where we had this 20 times slower one. So for a lot of applications, the JavaScript performance might just be enough for you, and you never need native C++ performance. But if you really do need native C++ performance, if you need this extra little bit of faster performance for really computation-heavy applications, you can totally do that in Node.js by writing a so-called native add-on. And I will not talk about that at all, because the next talk, Mariano's talk, goes into a lot of details about native add-ons. Just take away, you can write C++ in Node.js and use it exactly the same way like a JavaScript module. So where does WebAssembly fit this performance discussion? WebAssembly is a portable, size and load time efficient binary format for the web. It's a binary format. It's not a format that we humans write. It's a binary format. We write some other language and then compile it to binary WebAssembly. So the most common one is C, C++, but also Rust, Go, Lua, Java, all of those have a compiler now, so you can compile it to WebAssembly. And then WebAssembly runs in the browser. Since the V8 engine supports WebAssembly and V8 is a Node, you can also run WebAssembly in Node. And so I compiled the C++ add-on to WebAssembly and timed that. So the orange line here is WebAssembly. It's between C++ and JavaScript, so it's not surprising. There's a tiny bit of performance overhead for using WebAssembly instead of C++, but WebAssembly being a not dynamically typed language, it has pretty much the same performance profile as C++. So if you need performance, you can either use a native add-on for Node.js or compile your code to WebAssembly, which has the big advantage that you can also use it in the browser if it's not only a server-side project. So in summary, modern JavaScript is super fast. Yes, it's a dynamically typed scripting language, but for many use cases, it almost gives you native C++ performance. And it's great if you can use JavaScript because you have no overhead of having to use two different languages in a project. You don't have to learn two syntaxes. You can use all the same tools. Everything compiles and builds nicely. So that's a big plus. Native C++ add-ons are still a tiny bit faster. WebAssembly also gives you almost native C++ speed and has the big benefit of running in the browser. And as always, before you say, oh, let me rewrite everything in C++, it's faster, no, measure first, and then be very careful about your optimizations. Thank you.